So yesterday what we were discussing was magnetic circuits. We'll be continuing discussion about magnetic circuits. And let me start my presentation. Okay. Okay. So we are going to continue that discussion. Yesterday we discussed a little bit about what magnetic circuits are and how magnetism and electricity are both interlinked. Like electrical engineering is like a mother having two children. One is electricity, the other is magnetism. Okay, electrostatics is there, but that is one, a subdivision of electricity, if you can say. So these two children, these two sons of a mother are so very different but so very alike, but the mother likes both of them equally. You cannot say one is better than the other. They are interlinked also. One cannot exist without the presence of the other. That is how electricity and magnetism goes. And later on we'll come to a stage where it is found that they are together, they are mingled together, they are one and the same, like in the case of electromagnetic radiation, like in the case of the visual light that you are seeing, a rainbow, all those things are various forms of electromagnetism. They form together. Now, today's discussion, we'll be confining ourselves to magnetic circuits formed due to electric current. So, which means that yesterday, the main formula that we discussed was flux is equal to MMF by reluctance. I hope you remember, wherein we said we drew an analogy with the electric circuit, where flux, instead of flux we have I, current, is equal to EMF by resistance. And similarly we also said that reluctance is nothing but the opposition to the creation of flux, and certain terminologies which may require some definition for you will be, one is magnetomotive force, MMF. Magnetomotive force. Okay, so it drives, or how can you define MMF? MMF is something just like EMF, which drives or tends to drive magnetic flux through a magnetic circuit. EMF is something that drives, or that makes it possible for electric current to pass through an electric circuit. Similarly, MMF, or magnetomotive force, is something that drives or tends to drive or tends to create a flux in the magnetic circuit. And MMF, yesterday I discussed this also very importantly. MMF is actually equal to NI, ampere turns. Ampere turns. N is the number of turns, which is also equal to HL, where H is a magnetizing force of the magnetic field, and HL is the mean length of the magnetic circuit. And I also said that this equation essentially connects between the electric current and the magnetic field. So Ni is equal to HL, and in the case of EMF, we said that it is actually equal to the work done. Similarly, in this case also, MMF can be conceived as the work done in joules, can also be conceived as a work done in joules to, move a unit magnetic pole once through the magnetic circuit. When we discussed about EMF or voltage, we said it's a work done to move a unit charge from one point to other. Similarly, this can also be conceived like that. So that is regarding MMF. The next quantity that we are discussing about is reluctance. That also we discussed yesterday, but you may be asked to write the what is reluctance, what are the unit, etc. So it is opposition to the creation of flux, or it is opposition of setting up of a flux in a magnetic circuit. It is similar to resistance. And if you, in an electric circuit, you write R is equal to rho L by A. I hope you remember, which also you write as L by sigma into A, where rho is the resistivity. I hope you remember. What is sigma? It is the conductivity. Similarly, S is equal to, yesterday we discussed this equation, L by mu 0 mu r into A, or L by mu A, where mu A is the absolute permeability, mu 0 is the permeability of free space, mu 0 is 4 pi into 10 raised to minus 7, mu r is the relative permeability, or in effect what I want to stress upon here is that just like what is conductivity here, we have permeability here. Or actually, permeability is a measure of, when you say permeability is high, you say it is a measure of how much the flux can be created in a circuit. Or you can say the easiness with which the flux can be produced or created or set up in a magnetic circuit is called as permeability. Or it is almost the opposite of reluctance. Reluctance and permeance is permeance, 1 by permeance. Okay, this is permeance, permeance. Reluctance, sorry, reluctance is, yes, yeah, reluctance is the, or permeance is the inverse of reluctance. Permeability and resistivity and conductivity is something else related to by formula. So conductivity, whatever you have as conductivity in electric circuit, if the conductivity is high, electric current can flow with much easiness. Similarly, if the permeance is high, or if the permeability of a circuit is high, you can say that the flux can be created easily. That is exactly why we provide a core for a magnetic circuit. So all of you should listen to this point. This is a very important point, which it is a significant point which you have to, it is not directly written in any book, but you have to remember. See, if you have an electric circuit, or if you want electric current to pass from one point to another, you provide an electric circuit and it will be completed. How do you provide an electric circuit? You provide a good conductor and then you complete that circuit. And if you want to create magnetism somewhere, again you provide an iron core, or nowadays we have ferrite cores, or even Alnicol. So some core made up of a magnetic material. What do you mean by core? What I mean by core is something like this. Okay, a solid core or a laminated, whatever. And then what if I want to create a flux here? If I want to create a flux here, what I do is I provide a coil and supply a current like this. So depending on how many number of coils, Ni, I have my MMF in ampere turns, and a flux phi will be produced. Now, all of you should remember, why am I providing a core here? Even iron is, so I want most of the flux to pass through this circuit. But we know that unlike in the electric circuits, air is also a conductor of flux. Air does have some permeability. Air's permeability is mu 0, 4 pi into 10 raised to minus 7. So mu 0 is not 0. So mu 0 also has some value, means air also permits, or air is also permeable for flux. That has some other forms of problems also that we'll come to in a later stage. Now, what I am discussing now is about reluctance. Reluctance can be written as L by mu 0 mu r into A, and its unit is ampere turns per Weber. Ampere turns per Weber. Okay. So much regarding the terminologies used in electric circuits. Now the comparison. Now we come to the comparison section. As you all know, let's first think about the similarities. Similarities between electric circuit and magnetic circuit. or may rather we can write magnetic circuit first. Magnetic circuit and electric circuit. Okay. One, because you want to write so many points, you can always say the path of the path where magnetic flux is formed is called as a magnetic circuit. The path of an electric current is called as an electric circuit. These notes I'll give you. Then second thing, as you all know, flux is equal to MMF by reluctance. Similarly, you are having current is equal to, or electric current is equal to EMF by resistance. Okay. 3. The reluctance is equal to L by mu 0 into mu A, and R is equal to L by sigma A. What is A? What is A? Area of cross section. What is L? Mean length of the magnetic circuit or mean length of the electric circuit, whatever it may be. 4. Reluctance is equal to 1 by permeance, not permeability. Reluctance is 1 by permeance. Conductance equal to 1 by resistance. I am not speaking about conductivity or permeability. Permeance is different. Remember, resistance is different. This value. Okay. Conductance is equal to 1 by resistance, or resistance is equal to 1 by conductance. That is how it should be written, I think. Okay. Resistance is equal to 1 by conductance, or because I have written reluctance here. Okay, any more similarities? These are the similarities. Let us not waste time on these things. Then differences. Can anyone tell me the major difference which I was very much emphasizing? Differences. Differences between magnetic circuit, which is the most important difference. Anyone? Which is the most important difference between electric circuit and magnetic circuit? Advait?
Yes, ma'am.
Which is the most important, the significant difference?
Magnetic flux can pass through air.
Correct. That is it. There is no, I'll rephrase that in another way. Okay. There is no known, there is no known material that is a perfect magnetic insulator. Okay. Because air is also a magnetically conductive. Whereas in this, you know how to write. There are a number of good electric insulators. Example, air. Okay. Then second thing that you have to remember is, in the case of a resistance, suppose I have a resistance connected with a voltage source and a current is flowing. Or in the case of, even the electric bulb, heat is produced. Or I can say that I squared R heat or I squared R T if it's flowing for a time T. This is the energy consumed, isn't it? Or the power dissipated. I have used this word earlier also. This is wastage. Suppose it is used in a thermal furnace, or maybe if you are using an iron, electric iron, where heat is the outcome that is required. Heat is the product that you require. Okay, you are producing heat. Otherwise, this heat is lost to the environment, or this is a wastage of energy. It is, or you can even say that if you want to do something else with the current, it is being consumed, not only as heat. If it is producing light, that light is produced because energy is being consumed. Or I can say that electrical energy is consumed in an electric circuit. Consumed means in Malayalam നമുക്ക് പറയാം അത് ഉപയോഗിക്കണം അതങ്ങ് ഉപയോഗിച്ച് കഴിയണം. It is eaten up, okay, consumed by in an electric circuit. What about in a magnetic circuit? That is not the case. In a magnetic circuit, you can never say that the energy is being consumed, but energy is required to create the magnetic flux. Okay, create a magnetic field. Magnetic field means magnetic flux. You want to create a magnetic field. Usually, if it's an inductance that you're talking about, you will be inductive load. There will be a back and forth. You know, the energy will go from the source to the load, and then it comes back to the load, back to the source. So energy is required only to create or to maintain an magnetic field. It is not consumed at all. I mean, it is not maintaining it, like it is not consumed at all. The third thing is, my God. Third point that I want to tell you is, now in an electric circuit, resistance of an electric circuit is almost a constant. Resistance is almost a constant. I am saying almost a constant because it varies with the temperature, etc. But usually when you say that if you have voltage and current here, resistance is almost a constant. It is a slope. But what about reluctance? Now, if I have a BH curve, the BH curve it comes like this. I am sure all of you have learned. There is some part like a saturation. It is not always linear. As a result of this, the flux is also not a constant. Flux is not a constant means indirectly reluctance is also not a constant, because flux and reluctance are, so reluctance of a magnetic circuit is not constant because flux varies and flux density is also, because even in the same material, depending on the value of B and H, flux may vary. We'll come to that later on. Okay, and I think you will be studying in detail about saturation, etc. in electric rotation, electric machines also. Maybe in course of time I will also let you know. Okay, so that is all regarding the comparison of electric circuits and magnetic circuits. Now coming to problems. So first thing that they have given you is to solve series magnetic circuits. Okay. What are series magnetic circuits? What are series electric circuits? In series electric circuits, the current always passes, the same current passes through all the circuit elements. Similarly, in series magnetic circuits, the flux setup remains the same in all parts of the magnetic circuits. In all parts of the magnetic circuit, the flux remains the same. Such a kind of magnetic circuit is called series magnetic circuit. There is something known as composite magnetic circuit. The series magnetic circuit can also be composite. What do you mean by composite? Composite means the magnetic circuit is consisting of different materials at different points. It may be iron at some point, maybe some other ferrite at some point. So the magnetic material, the flux remains the same, but the material may change. So if the material changes, as you know, mu will vary. Let's see, one very, very simple problem. I want all of you to write down this problem, please. First problem. After doing this problem, we'll have an interval and then we'll come back. Okay, after doing this problem. An iron ring, you may write please, an iron ring of cross-sectional area, an iron ring of cross-sectional area cross-sectional area A is equal to 6 centimeters squared is wound with a wire of 100 turns. Is wound with a wire of 100 turns and has a saw cut. Just check your screen. Saw cut. Saw cut means they have cut through the iron. Okay, saw with a saw. A saw cut of 2 mm, 2 millimeter. Calculate the magnetizing current. Calculate the magnetizing current required to produce a flux of 0.1 milliweber if the mean length of the iron path is 30 centimeters. 30 centimeters. The relative permeability of iron is given as 470. Okay. I'll read the question once again. All of you should check whether you have written everything correctly. An iron ring of cross-sectional area 6 centimeters squared is wound with a wire of 100 turns and has a saw cut of 2 millimeters. Calculate the magnetizing current required to produce a flux of 0.1 milliwebers if the mean length of the iron path is 30 centimeters. The mu r, or the relative permeability of iron, is 470. So, area of cross section capital A is given as 6 centimeters. I want to convert it into meters. So 6 into 10 raised to minus 4 meters square. Centimeter square, centimeter square. So minus 4 meters square. The number of turns is given as 100. You are asked to find out the magnetizing current, I. Flux is given as 0.1 milliweber, which I have to write in Weber as 0.1 into 10 raised. Milli means minus 3 Weber. Okay. Now length, and it has a saw cut of 2 mm, which means how can I draw this? I have an iron ring of a certain area. Okay. Oh God, it came out almost good. Okay. Normally, when I draw a circle, it will not come at a circle. That is my weakness. Okay. So they have cut through this using a saw. So that is 2 mm. Or I can write that. So when it is cut, what do you have there? It is an air gap. This is called as an air gap. Or length of air gap, LG. Length of air gap is 2 mm, which I can write as 2 into 10 raised to minus 3 m meters. Any doubt? Because they have cut through the iron path or iron ring, you are getting an air gap there, only so small. Though I have drawn it in a bigger manner, it's just small, 2 mm. And the rest, because they have mentioned, all of you should read the question once again. They have mentioned that the mean length of the iron path alone, LG, that is excluding the air gap, is given as 30 centimeters, which I can write as 30 into 10 raised to minus 2 meters. Is so much clear for all of you? And they have asked you to find out what is I, which means I will be having a coil here through which I will provide a current I, and the coil is having 100 turns. I am asked to find out what is this I. I am asked to find out this value of I. Okay, that is a question. Have you all, Rishikesh, have you done such problems in +2 level? Rishikesh?
Yes, ma'am.
Have you done similar problems in +2 level?
Yes, ma'am. Kind of
Yes,
similar.
okay. Okay. So my task is easier. Okay. So is this a composite electric circuit? Is this a composite electric circuit? Someone, no, if your answer goes wrong also, I don't have, it is okay. It is for my, my satisfaction. Nandana PM. Nandana.
Ma'am.
Nandana, is it a composite magnetic circuit? It is a series magnetic circuit because flux will be formed here, and through every part the same flux flows. Okay, same flux is formed. I cannot say flow. It is formed. So which means it is a series magnetic circuit. Okay. So my question is, Nandana, whether it is a composite magnetic circuit as well? Nandana?
Yes, ma'am.
Why do you say it is a composite magnetic circuit? Because this part, you have two kinds of material here. One is iron, the other is air. Okay, air na namukku vela kodukkadirikkannu. Nandana.
Okay, ma'am. Okay, ma'am.
Nandana, ഈ ഓക്സിജൻ ഇപ്പൊ ഭയങ്കര വിലയാണ് കേട്ടോ. അല്ലേ? So air ആണ് എന്ന് പറഞ്ഞ, don't take air as taken for granted. It is really the most important thing in our life, isn't it? So because so Nandana, you missed that point. I think you missed that point, alle?
Yes, ma'am.
So composite magnetic circuit means made up of different materials. So the flux is passing through iron at certain points, and the flux is passing through air also. So this is a series magnetic circuit because the flux is formed in all formed in all parts of the magnetic circuit is the same. It is a composite magnetic circuit as well because two kinds of materials are coming in the series circuit. One is iron and the other is air. Now you are asked to find out I. There are different ways in which it can be approached. I think the easiest method will be to approach it as I tell you now. Though the calculation, because that is what will make it more understandable for you. Now what I am going to do is, I will be finding out the total reluctance of the circuit. The total reluctance of the circuit. And finally what I'll do is, Ni, I know that these equations will be used. That is, Ni is equal to, Ni by S is equal to flux. Flux phi is equal to Ni by S, that I know. Ni is mmf by reluctance, that I know. So flux is given. If I can find out the total reluctance also, flux is given as this value. And if I can find out the total reluctance, N is also given. The only unknown here will be I. That is how I am going to approach. Okay, so that I can find out I. So first I have to find out the total reluctance. S total. S total could have been found in one step had there been no socket, had there been no air gap. But now what I have to write is S total is equal to, that is reluctance of the iron part plus reluctance of the air gap. So reluctance of the iron will be Li by mu0 mu r into A. Area of cross section remains the same. So we do not have any problem. Area of cross section is the same. Area is given as, or A by A plus Lg by, I just need to write mu0 here because mu r is equal to 1 into A. Both these things are the same. So I substitute. Li is 30 into 10 raised to minus 2 divided by 4 pi into 10 raised to minus 7 mu naught into 470 mu r into area is given as 6 into 10 raised to minus 4. 6 into 10 raised to minus 4, that is of iron, plus Lg is 2 into 10 raised to minus 3 by 4 pi into 10 raised to minus 7, no mu r, into 6 into 10 raised to minus 4. I want you to find out these two separately. Do you have your calculators with you? If you don't have your calculators with you also, it is okay. I'm giving you, this is 10:05 now. You can take a break till 10:20 and come back and join me. What are the timings? I forgot. What was 10? I have time till 10:45. 10:20. Okay. Join by 10:15 with these two answers separately. Okay, that's all for now. We'll meet again at 10:15. 10 minutes break. Okay.